Welcome all. Welcome to today's online class. Today we discuss the third law of crystallography, that is law of rational indices. Before we go into the law, we have to get familiar with a few important terms in connection with this. First of all, crystal plane. You know that in a crystalline solid, particles are arranged in a regular repeating order or pattern. Suppose this is the unit cell of a crystal, which is cubic in shape, and this unit cell repeats along the three axes x, y and z to build up the crystal. So imagine that there are so many lattice points, and it is about this point the constant particles or motifs, which can be atoms, ions or molecules, are arranged. Now crystal planes means there are a number of parallel planes which we can draw in a crystal. For example, look at this. I can draw a plane. Let us consider a plane passing through these particles. So planes passing through the motifs, there are so many, because if this is a plane, you can see in the next unit cell there will be another plane and it repeats. So crystal planes are the planes which are parallel, number one. Two, equidistant. See, between these two planes, this is one plane. Okay, I am considering this plane, for example. There is a parallel plane here, and that will repeat in other unit cells. So crystal planes are parallel as well as equidistant. So that is crystal plane, parallel and equidistant planes passing through the constituent particles in a crystal. And you can have so many different types of crystal planes in a crystal. Let me take another. See, one is this plane I am considering, and this is a parallel plane. It can go like that. I can take this plane parallel to this. There can be a number of planes. Many different planes are possible. Now, next term is crystallographic axis. See, in a crystal there are a large number of parallel and equidistant planes. Now, to describe the direction as well as orientation of these planes, we need to choose three axes which are called crystallographic axes. So three axes are chosen which meet at a point, that is origin, using which we can describe various planes in a crystal. For example, this is a cubic crystal. Let me consider this as the origin, and let me show the crystallographic axis as just like the normal Cartesian coordinate. This is x-axis, suppose. This is y-axis, and this is z-axis. You can see, right? X, y and z-axis. Of course, it will have a positive side and a negative side. If this is plus x, this will be minus x, like that. Now this is the origin. Okay. Now, this crystallographic axis, here see that these three axes x, y and z are mutually perpendicular with an angle 90 degree. It need not be so. In different crystals, these axes can have different angles between them. Okay. Now, it is that various crystal planes may intercept or cut these axes, one or more axes, or it can remain parallel. That is the relation between the crystallographic axis and the crystal plane. For example, consider this plane. Okay, I am considering this plane, this crystal plane passing through these four constant particles. You can see that this plane is cutting which axis? X-axis at this point, correct? So this is the intercept along x-axis. What about y-axis? It is not cutting. Y is going like this, plane is going like this, it's parallel. So a plane can intercept an axis or it can remain parallel to it. When it is parallel to an axis, we say it cut at infinity. It intercept at infinity. Similarly, you can see here in the z-axis also this plane is not cutting, not intercepting. So a crystal plane can cut one or more crystallographic axis or it can remain parallel to it. Now we consider unit plane. What's a unit plane? So let us draw a cubic crystal. You know the simple way of drawing a cubic crystal. Draw a square and another a little displaced. It's very easy. We'll be drawing so many cubes in this module, remember? So you should be very quick in that. So this is a cubic crystal, suppose. And let me consider the crystallographic axis here. Suppose I am considering this as the origin. So it goes like this. This is x-axis and this is y and this is z-axis. Let me define what is unit plane. It is a crystal plane which intercept all the axes. That is the point. Unit plane is a plane which cut all the axes. So let me consider example. Let me consider there are particles, suppose, at these points. Okay. And let me draw a plane connecting these three particles. Right? Remember, this is the origin, this is the origin. And let me mark this plane as A, B, C. Right? Now, suppose OA is small a, that is the intercept along x-axis. Along y, this length OB is B, OC is C. Right? So this plane, let me mark it. This plane, it's looking like a triangular plane. So this plane ABC, this is a unit plane. Why? Because this plane you can see is cutting all the three axes, x, y as well as z. This is a unit plane, a crystal plane which intercept all the crystallographic axes. Right? Now, next is lattice parameters. See, every crystal is characterized by its lattice parameters, which include one, axial ratio or axial distance. The second parameter is axial angle. Actually, it is based on these properties. Crystals are classified into 7 crystal systems, cubic, tetragonal, etc. Axial ratio is this ratio, that is the ratio of the intercepts along the three crystallographic axes, that is A is to B is to C. This is called axial ratio. The ratio of the intercepts of the crystal plane, unit plane. And axial angle is, what is angle between the three crystallographic axes? It is represented as alpha, beta, gamma. Alpha is to beta is to gamma. You might have learned in your plus 2 course that a cubic crystal is characterized by the lattice parameters A equal B equal C, correct? A is equal to B equal C, that is cubic, right? All the sides are of the same length, and alpha equal beta equal gamma, and this ratio is all equal and it is equal to 90 degree. That is a specialty of cubic crystal. Like that, different crystal systems have got different lattice parameters. Now, how we define alpha, beta, gamma? It is like this. See, opposite to this A, we take the angle alpha. Opposite to B, we take beta. Opposite to C, we take gamma. Okay, that's how we take the angles. So that's about lattice parameters. Now we come to the law, right? What does this law of rational indices says? It is talking about the crystal planes, right? And how we represent various crystal planes in terms of unit plane. That is the law about. The law says that the intercepts of any plane, any crystal plane, can be represented, the intercepts of any plane along the crystallographic axis can be represented as integral or rational multiple of the unit intercepts, the rational multiple of unit intercepts or the intercepts of unit plane. Unit intercepts. Very simple law. So it is that the intercepts of all the planes can be represented in terms of unit intercepts. It will be an integral multiple, that is, it will be a rational multiple, a rational number multiple of the unit plane. So it's so simple. To explain this, we can consider a very simple system, a simple diagram. See, without considering the shape of the crystal, let us consider the three axes x, y, and so let me draw z like this. Actually, z is out of the plane, perpendicular to both. And here, let me mark a unit plane. Suppose, for example, like this. See, this is A, this is B, this is C. Like this, I mean, this is a unit plane. I'm marking A, B, C is the unit plane. So what about the intercepts? You know, this is small a, small b, and small c, right? So the unit intercepts are unit intercepts or the intercepts of unit plane. Unit intercepts are A is to B is to C. Okay. Now let me draw another plane. Okay. I am considering another plane in the crystal. Suppose it is like this. I am marking one point here. There is a particle there. And suppose there is a particle over here. And let me extend this a little more. This is Z axis, and let me mark here. Suppose it is here, like this is 3C, for example. That is at the point, and let me now, okay, of course this point is somewhere here. Let me connect this to get the given plane, another plane. I am marking it as A dash, B dash, C dash. Now for the plane, so this unit plane is A, B, C, and the intercepts are small a, small b, small c. Let me consider the plane A dash, B dash, C dash. What does the law says? The intercepts of this A dash, B dash, C dash can be represented as an integral multiple of this. It's so simple, because what about this OA dash? This is origin, of course. It is 2A. Because this is A, this is 2A. And this is 2B. 2A is to 2B is 2. This is 2B. And this is, suppose it is 3C. So the intercepts are 2, 2, 3. 2, 2, 3. 2, 2, 3. Or 2 is to 2 is to 3. So it's a simple rational multiple. Right? In other words, this law can be stated as, if the intercepts of a given plane is PQ, it is PA is to QB is to RC. Suppose the intercepts of a given plane is like this, where A, B, C are the unit intercepts. Then the law says that P, Q, R will be whole numbers or integral numbers, rational numbers. Okay, so that is the point. Now here we introduce a term that is Wiess indices. What is it? These intercepts, the whole numbers, the intercepts of a given plane is called Wiess indices. So that's to be noted now. What is Wiess index? Wiess index, the plural is indices. So remember this plane, the one which we have just drawn. From that we know the plane which we consider is A dash, B dash, C dash. That is a plane under consideration. And we know the intercepts we have just got is 2A, 2B, 3C. Now we define what is Wiess indices. It's so simple. Wiess indices are the intercepts of a given plane along the three crystallographic axes. The intercepts. The intercepts of a crystal plane along the crystallographic axis. Along the crystallographic axis. Okay, it is represented using as letters PQR. PQR. Sometimes put in bracket. We represent a plane using putting in a bracket. So PQR is the Wiess index. So what is the Wiess index in the example which we discussed? The Wiess index is 2, 2, 3. That is the Wiess index. Okay. But okay, let me consider another example. See now I am considering a cubic crystal. Okay, the plane in a cubic crystal, suppose. As before, let me mark the axis. This is X, this is Y, this is Z, this is the origin. I am marking a plane. Okay, you should tell me about this plane. This is a plane which I have marked. What is a Wiess index for this plane? See this plane is cutting this axis only and parallel to this Y and Z. And suppose this is A. So we can say it is 1A, right? It is 1A, comma. What about along B, if this is B and this is C, it is not cutting B, so we have to say it is infinity B, because I said when a plane is parallel to an axis, we say that it cut at infinity. So infinity B, and it is again parallel to a Z axis, so it is in infinity. It's infinity, okay, not alpha. Infinity C. Also, what is the Wiess index here? 1 infinity infinity, which is undefined. So here we feel a better term for representation. That is what is Miller indices. So the crystal planes are better described in terms of Miller indices. Okay. So what is Miller indices? It's very simple. It is just the reciprocal of Wiess indices with fractions cleared. Okay, that is Miller indices. Miller indices. It is represented as HKL in bracket. So Miller indices of a crystal plane is represented as HKL, where HKL are the reciprocal of Wiess indices with fractions cleared. Let's take the first example again to explain Miller indices. We have seen that the intercepts for the plane A dash B dash C dash is what? 2A, 2B and 3C. And the Wiess index is 2, 2, 3. How to convert Miller index into Wiess index? In 3 steps. How to determine Miller index? In 3 steps. Step 1, write the intercepts. What are the intercepts? Intercepts of the plane. It is 2, 2, 3. Second step, take the reciprocal. To convert into Miller index, take the reciprocal of the Wiess index. So it will be 1 by 2, 1 by 2, 1 by 3. And third is clear fraction. Clear the fractions. So what you multiply the common factor will be? Multiply by, it will be I think 6, right? Multiply by 6, it will become 6 by 2. So that is 3, or let me write 6 by 2, 6 by 2, 6 by 3. That is equal to 3, 3, 2, or the Miller index is 3, 3, 2 in bracket, right? So 2, 2, 3 when taken as the reciprocal and cleared fractions, 3, 3, 2 is the Miller index. So you may wonder why we need Miller index. Okay, to understand that, let us consider the second example, which is the down. Here I told you this plane, what is the intercept? 1, infinity, infinity. It is undefined. So what we do? Take the reciprocal, 1 by 1, 1 by infinity, 1 by infinity. What is it? 1, 0, 0. The Miller index of this plane is 1, 0, 0. This plane is represented as 1, 0, 0 plane. It is defined now. That is the purpose of making converting Wiess index into Miller index. Suppose I am considering another plane. Look, I am taking this plane. Tell me about this plane. What are the intercepts here? For this plane cutting along Y and parallel to X and Z. So we can say the intercepts are infinity A, 1B, infinity C, correct? So it comes infinity, 1, infinity, taking reciprocal, 1 by infinity, 1 by 1, 0. Actually these are equivalent planes. Writing 1, 0, 0, 1, 0, 1, 0 or 0, 0, 1 are all equivalent planes. See, taking X, Y, Z is our choice. You can take this as X, this Y, this Z in any way. So these planes are all equivalent. Now let us do one question on identifying Miller index of a plane. The question is this, you may write down. Calculate the Miller indices of a crystal plane which cut through the crystal axis, and there are many questions. The first question is the intercepts are given 2A, 3B, 2A, 3B, comma C. Okay. Then the second question, the intercepts of another plane is half A, half B, comma infinity C. And the third question, 2A minus 3B minus 3C. See, the intercepts can be minus also when it is going the other side of the axis. So how to find the Miller index? I think you can do it. Let me do the last one, or let me tell you that when you get the answer, when you get the answer as negative, in the Miller index it is put as bar. Like for example, if there is minus 3, when you write in bracket, it is written like this, 2, 3, bar 3, not negative 3. That is a point to be noted. So you can easily determine the Miller indices of all these in using the same 3 steps. Okay, so that's the end of it. Thank you.